the machines did the XOR first and then the permutation. You can check that for certain things in the analysis it doesn't make a difference, and for other things, well, you can check it later. Like you can work with it, and then you will get a little bit. You get a certain error in the key stream you would deduce, and then you would check it against something else in the end and find out, oh, this doesn't work out, and you would go back and try the other way and then find out that this works. I'm going to save you that and tell you right now that it's not this case, it's this case here. First XOR, then permutation. But we got the idea for the permutation from, well, the moving around of these characteristic bits here. Okay. Now, well, we know we've got an XOR and we've got a permutation. One question, which is slightly technical, is no, actually, okay. Now let's first try. I'm sorry. Let's first try to actually find out which permutation was used in a certain column of your intercepts, and you can do that by, well, finding these characteristic pairs of characters which have only one single 0 or single 1 in their difference. Because then you can look at the difference between the ciphertext and the assumed plain text and see where the characteristic bit has moved. So you would know, for example, in this before here, oops. Here you can see, well, this is your assumed plain text. This is your assumed ciphertext. So you see that the 0 here. You know that, like I said, they should be the same if it was just the superposition. These should exactly be the same. So you can see the permutation moves a bit from position 3 to position 2. So you can see, well, one part of the permutation is moving bit 3 to position 2. And if you do this for different pairs of characters which have the characteristic bit in another position, then you can deduce the entire permutation, because the permutation can be broken up into individual. You can just see, well, this one moves here, this one moves there, and so on, and you'll know the permutation, right? And what you need is only 4 of these characteristic bits, because it's 5 parts, and if you know where 4 of them move, well, there's only one possibility left for the last one. So you only have to find 4 of these pairs, and, well, we're lucky. I told you before that the QRV was also a very common thing in the texts, and actually combining 3, 5, and QRV gives us 4 pairs that will do the trick. You see 3, 5, I already showed you, has the characteristic bit in position 3, then 3Q gives the 4, QR gives 2, and 3V gives 1. And then the 5th bit is obvious where it moves. So you can deduce the entire permutation by finding these 4 pairs in one row of your intercepts, right? That is, you have a few messages encrypted, or a few plaintext characters encrypted with the same key. You know that because they're in the same position in the intercepts, and you just look at where you take the ciphertext corresponding to these plaintext characters, XOR it, and see where the characteristic bit ended up. Okay. Well, maybe I should go back to the picture. It might make it a little easier to understand. Right, so here you see GU35 in this row. That is, you know, this has the same ciphertext, the same key, and well, you look at the 3, 5, you know they have their characteristic bit in position 3, I think, and you look at where is it in GU, right? You XOR GU, and then you see, okay, it's in position 2. So you have one part of this permutation for this column, and then you can do that. Then if you find in this column more of these pairs of characters that I just showed, then you can find the rest of the permutation for just this column. And then you have to do this over for the next column and so on. This is a tedious process, obviously. You'll have to make some guesses here and there, and but in the end you will find enough of these things. If you have like I don't know, like 20 messages or 30 messages, they would, I think, receive up to 100 messages with the same key on a day. So they would have enough of this stuff, and you only need to do it once, because afterwards I'll show you that you can figure out the entire machine state and then do it all automatically from there on. So so you have to do a little guesswork in the beginning in order to guess enough of these things. Note also that once you find the key for one of the columns, right, it's completely clear what the rest of the plain texts are. You can just once you because these are have the same keys, the same key, well, words or characters, and then you can. It's like filling out a crossword puzzle, right? You know the key from somewhere here, and then you can fill in the rest of the column, and then you can probably guess more words, and then the words stretch over to in this direction, and you have more columns which you can work with, and maybe you'll figure stuff out there. Okay, so right. So let's assume we've uncovered a lot of these permutations, and the question becomes, well, how are the key stream bits actually generated, or how is the permutation generated? Well, the key stream bits are probably obvious. It's safe to assume that they are done with pinwheels because this was the known technology of the time, and well, we can assume that Arne Beuerling did this. He assumed that they were using pinwheels for the 5 key stream bits for each character, and the question is now, what do you do for the permutation? Because this was something new. And then we know that he said he remembered seeing relay switches used in telephone exchanges. You would have a relay switch which would, depending on the input, choose one, well, send, well, depending on an input bit, it would either cross, no, it would send the current in a wire either one way or another way. And if you combine 2 of these switches in the right way, you can build cross switches that would have an input of 1 bit and take 2 wires, and depending on the bit, they would either cross the wires or just pass them through. So you can have basically, and these would, so if you take your 5 signal lines in the teleprinter, and you want to permute them somehow, the signals, you can put cross switches in between these the individual wires at some positions, and well, transpose the bits that way. So this gives you, in theory, any permutation you want, because you can decompose every permutation into a series of transpositions. And then you could use pinwheels again to generate the inputs for these cross switches. So so this is the next assumption that would be made. Well, okay, they're probably using this kind of switch, and then they're probably, or almost certainly, they're using pinwheels to generate the inputs for them, and thus they get this random permutation. The question then just remains: how many switches do we have in the machine, and in what arrangement on the wires? Because we see the permutation, we see the result of the switches, but we don't see the input bits for the switches. And this is what we want to know, because we want to know the actual machine state. So, and also it's likely, or it would appear likely, that they wouldn't put a full set of cross switches on the wires, like because these were not exactly small. They were actual relays, and 2 of them probably for each switch, and so on. So it might be, well, it might not be a ton of them, but only some wires possible to be transposed. So, but well, we can find this out pretty easily by just looking at the permutations that actually do appear, because we know we can decompose them into transpositions. Well, let's assume, well, we have 5 wires. Okay, so we have these permutations with 5 elements, and let's say we've discovered a ton of them by this manual method mentioned earlier. Then you just decompose these transpositions. You can uniquely decompose them into these cycles, and then you can split them up. So you would know, okay, we have this this permutation here. This notation is supposed to mean bit 1 is sent to position 5, bit 2 is sent to position 3, bit 3 to position 4, and so on. And this is supposed to be the transposition which exchanges bit 1 and 5. This is supposed to be a cycle that puts 2 to 3, 3 to 4, and 4 to 2, and so these are, and then it's split up in this way. Not exactly important, the mathematics, but the important part is that you can decompose the permutation here into 3 transpositions, and that way you can deduce that, well, the machine will have to be able to switch wires, to cross wires 5 and 1, 2 and 3, and 3 and 4 in order to implement this permutation. And if you do this a couple of times, you will find out that, well, there are never more than 5 transpositions involved in the whole thing, and so you can assume there are only 5 switches, and you would know because you see which ones you need, and then you could make a very good guess at that a certain pattern of cross switches was used. For example, like this. This matches with our example. These are supposed to be the 5 wires. These are supposed to be the 5 signal wires, and each X represents one of these cross switches. Well, so this is the 1, 5, and this is the 3, 4, this is the 2, 3, and then an additional 4, 5, and 1, 2. So these 5 switches, this would be a typical setup, and you could discover this just by looking at the permutations that actually appear. So now, well, we know pretty much what the machine is built like. We know it's a we know we have these pinwheels, and we have these permutation switches, and then it's basically just well, it does the XOR and the permutation, obviously. Now, well, it has 10 pinwheels. That's what we know now, because we know we're pretty sure that we need 5 keystream bits for each character, and we need 5 bits for the permutation for each character, and it's safe to assume that the machine processes 1 character each cycle, because that's the way these things worked. Okay. So we'll assume that the T52 has a drum of 10 pinwheels inside that generate 5 bits for the keystream and 5 bits for the permutation. Now, the only thing that's missing for us to be able to, well, say, build our own T52 would be to know the patterns on the pinwheels. I said that, well, the pinwheel is inscribed or circumscribed with a pattern of random bits. So we would have to know these actual patterns, but they're easy to find. If you decipher a long sequence of text, like the one I showed in the example, you will find the permutations, and because we've deduced the switch arrangement, we know which bits the wheels will have generated in order to produce this permutation. And well, we also know the key,